if we could go through like part of exercise 5 on the homework with like it's like putting an FSM and like using the output of that to be an enable on another module. Like, or if we could go through like some sort of example similar to that. It doesn't have to be obviously the homework, but
Okay. Yeah, I'll go ahead and open that up and take a look at it. You said it was homework 20?
no, this is 19.
19. Okay.
Good Noodle, have you finished that problem on the homework yet? Or
No. Not yet.
okay. Yeah. I know it's now due Wednesday, I think, but I don't know. I kind of was like wanting to get a jump on it.
Yeah.
Okay, so I assume it's the. Is it exercise 5? Is that the one?
Yeah. Um yeah, so it like we wrote the BCD earlier. Um and now we just need to like add an FSM to it. Yes.
Okay. I'm between counting. Okay, cool. So the basic idea is you have a thing you're trying to control. In this case, it's a binary coded decimal counter. And you're essentially trying to make it so that you can make it start counting or make it stop counting and stay the same. And that's all going to be determined by a single button press, which essentially is going to be the input of an FSM, and the output of that FSM is going to be an enable signal that either allows or disallows a BCD counter to count. Does that sound all right by you guys?
Yes, that sounds good so far.
Okay, so I'm going to go ahead and draw a little bit of part of the FSM up on the board, starting with the first. Rotate this. So, is that a little better? I know it's a bit difficult to see because it's sideways. Can you guys read that?
Wait, sorry, I can't hear anything you're saying yet.
What about now?
Better.
Oh, yeah, that now that's fine. Yeah.
Yeah, it just has to be facing me. Are you guys able to read this? Because if not, I need to move it a little bit.
I can read it.
Yeah, I can read it.
Good enough. So, when you begin, your BCD counter is, in some state. I'll just assume that it's not counting initially. That's a choice that you as the designer needs to make, but for me in particular, I'm just going to assume I want it to start to not count at the beginning. So in this state, I would assert my output as enable equals 0. And from there, I would go ahead and start filling out the rest of my states. So in this state, if I don't receive a button press, I'm going to stay here indefinitely. So I'll go ahead and have the signal A represent a button press. So I'm going to go ahead and put him. So while I haven't received a button press, I'm going to just stay here. Nothing's going to change. I'm still not going to be counting from my BCD counter. However, right when I receive a button press, I need to go to a new state. So when I press the button, the output goes from a 0 to a 1. And then when I release the button, it's going to go back down to a 0. And I want this to count as a single button press. So I get a 1, and I'm going to stay in this state. And I'm going to stay in this state while this remains high, because remember, the entire time this is high, this is supposed to correspond to a single button press. So I'm going to keep residing in this state. It's going to stay in that state indefinitely until I let go of the button. Now, while I'm in this state, I want to count this as having been pressed. So the button has been pressed, which is to say I'm going to basically enable or allow my counter to count. And once I release this, I will have finished my button press. Now I still want my counter to be enabled after this button press. But I do want to move to another state because now I've finished reading in the top part of that button press, the highest ordered part. So once I get my end of my button press, that's this A bar, I'm going to go over into the next state. I'll call this S2. So here's when it's being actively pressed. Here it's not being actively pressed, but we've switched from enable 0 to enable 1. So I'm going to stick with that. And again, I'm going to stay here until someone presses the button. So I'm going to be staying here. So I'm going to stay here until someone presses the button again. And once they do press the button again, now I have to go over to another state. And the same deal applies here. I want to transition to this next state, assuming I've received a button press. But when I've received a button press, I want to essentially count that entire time as being high as one button press. So I'm going to stay here while the button is still being pressed. So I'm going to stay here, stay here, stay here until the person who's pressing the button lets go. And now I can move on to the next state. So now I transition over here, and my enable is 0. So the way this works is, if initially let's see. So here A looks like a clock signal, but it's just supposed to be essentially someone pressing or depressing the button. And enable here is going to correspond to whether or not we are enabling our BCD counter to count. And in actuality, we do have a clock signal here running our FSM, and it's probably going quite fast, much faster than I'm able to draw. But it's going to be acting very, very quickly. So it would be more like a sporadic line here that I can't quite draw. So assuming we started in the reset state, enable is going to start at 0, but as soon as we press the button, it's going to go up to a 1. And it's going to remain a 1, and it's going to remain in the state while the button's high. And even after the button goes low again, we're going to move over to the state here, where enable's still on. Only once another button press is detected do we move on to this next state, where we have that our enable is going to be off, it's going to be 0. So as soon as we have this other transition, our enable is going to go off again. And so after one button press, we switch it on, and after a second button press, we switch it off. And so that's the idea of this this FSM. That's what they wanted you to do. So any questions on that?
Can you give me 1 second?
Yep.
Okay, yes, I think that makes sense.
Got any questions for me, Good Noodle?
No questions.
And so the idea here is, your clock is off running very, very quickly. And like I mentioned, we don't want every time we read in a 1 to assume that it's a new button press, which is why we have these series of 2 states. So we have a state to essentially read in all of the 1s until we transition back down to a 0, and then a state where we remain in 0, waiting for another button press to occur. And both of these states together correspond to the enabled state. Same deal for these, except for the disabled state, or when enable's off. So this is the entirety of the FSM, and all you would really need to do after this is noting that you have your BCD modules already finished. You would need to add an enable signal to those BCD modules, basically to let them count if enable's on and to disallow it otherwise. And all you'd really need to do is the following. All you need to do is take the FSM, hook up the input button, and as well as the clock, and then you can output the enable signal, the output logic of the FSM, into the input enable signal of the BCD counter. And that's pretty much it. Any questions?
So would the FSM would be its own structural module component? And
Ideally,
then
that's how you'd make a
yeah, because I just like part E has like the entirety, like the main program, the stopwatch. So I'm just looking and it's like we have an S, but that would be our enable, right?
um. Let me see. Oh, well, sorry, that A was S.
Right. Okay.
But
But oh, so A is S, but not the enable. The enable is not the S part.
yeah, enable's just an internal signal that goes between the FSM and the binary coded decimal counter.
Oh, right. Okay.
Any other questions on this?
I think that should be a good start. Like I was thinking of the FSM like totally differently from what you drew, so I think this will be a good start.
Cool. Okay, are you guys alright if I erase this then?
No problem for me.
No problem for me either.
Yeah, did you guys have any other questions for me?
I'll let Good Noodle go first because I do have another question.
I don't really have a question, but I just want to say thank you for because when we had our last talk, and you said about making the game clock its own module, that's why I did, and it's working. Thank you very much.
Excellent, good. I'm glad to hear that. So what was your question, Shauna?
So my question, like, I'm really struggling with the whole test bench thing. And I was wondering if we could do like walk through exercise 2, given like a BCD counter, and I don't know, I can like shoot you what we came up with for the BCD counter, like what the inputs are and everything, but
I'll go ahead and, well, this will actually be easier for me. So I'll go and share this for you. Tell me if you guys are able to see my screen. I'll let you know what it should be at. And then we can talk about how to write the test bench.
wait, I'm sorry, there was a lot of noise on my end. I didn't hear what you said before, like we can talk about the test bench.
Yeah, I was just saying that I'm gonna put it up on the screen so you guys can see me typing it. That way I don't have to handwrite it. It'll be a lot easier.
Oh, okay. Okay.
Oh, I'm just making a file here. Very cool. So can you guys see the screen? I know it's a little weird. I can edit and change like the shapes and stuff, but are you able to see the screen?
Yep.
Yes.
Let's do it like this. There. And also that. All right. So as with any other module declaration, you always want to say module, the name of the module, followed by the port list. But in this case, because it's a test bench, you actually don't need to have anything in the port list. You have your end module at the bottom. There we go. Okay. So when you're doing a test bench, there's typically a few things you need to get out of the way first. So one of the primary things is you want to create all of the internal logic signals that your device under test is going to need. So in this particular case, if we were to look at the assignment, we have a module BCD counter. So I'm going to copy paste the port list for it into here. So this is my module that I would be testing. I'll actually go ahead and move that down here. So this is the module that we would be testing, and we want to create a bunch of internal logic signals to go into each of these different parts of my port list. So I'll go ahead and write those up. We want to say logic, and then we can say clock and reset. And then we also want a 4-bit signal, so 3:0, and that's for the count. And so now what I can do is I can actually instantiate a device under test. I can instantiate my BCD counter. The way I do that is I just say BCD counter, which is the name of my module, and then I would give it the instance name, which in this case I'm just going to call it DUT because it's my device under test. And then I would feed it the specific input signals, which are these ones that I've made. So after making your internal logic signals, as well as your device under test. The next thing you want to do is you want to essentially generate your clock and pulse your reset for the circuit. So the first thing I'm going to do is generate my clock. So the way you can do that is you can just have something like an always block. I'll do always begin. So in this block, I'm going to go ahead and generate my clock. And the way I'm going to do that is I'm just going to say clock is going to initially be 0. I'll go ahead and wait 10 simulation ticks. So that's what that #10 sign means. That means wait 10 simulation ticks. And then I'll set clock to 1, and I'll wait another 10 simulation ticks. And because this is an always block, it loops indefinitely. So it's going to set it to 0. It's going to set to 0, wait 10 simulation ticks, go to 1, wait 10 simulation ticks, and then repeat 0, 1, etc. And so that's how we can generate the clock. And we just want to leave it like this because the clock is supposed to be consistent and repetitive, so we'll just leave it as is. And the next thing we have to do is pulse the reset. So the way you can do that is with an initial block. So unlike an always block, which repeats over and over again, an initial block just occurs right at the beginning of your simulation. So I can say initial, begin, end. And so in here, now I can actually go ahead and pulse my reset. So I can say, well, I'm going to say reset is going to be equal to 1 at the very beginning. And I'll go ahead and wait 25 simulation ticks. And then after that, I can set reset back to be 0. Okay, so any questions on this stuff so far?
So I do have a quick question. Like I noticed that in like some of the examples we were doing, there'd be a clock and a reset like in the port list of the main program, but then in the test bench it would just be like the bare inputs and outputs without the clock. And I guess like my question is, why do we sometimes include device under test like clock and reset and sometimes we don't?
So are you saying like an example where the BCD counter has a clock signal,
No,
but we don't put it in here, or the opposite?
no, it wasn't for the BCD. Like it was for
But like just a general module, I mean.
general like combinational logic, and it maybe that's why it's because it's just combinational. Um,
Well, yeah, I mean, if it is combinational, you don't need a clock. The only thing you'd need a clock for would be if you were just for like the purpose of the test bench to see the different tests occurring at each clock like interval. That's the only reason you would use a clock. And for most test benches, you will probably see a clock even for combinational logic. Not all of them, though. You don't have to have one. It's not strictly necessary.
okay.
Any other questions up to what we have so far? So now that we have, okay, go ahead.
No questions.
Okay, cool. So now that we have this kind of introductory part of the test bench done, we have a few options. So we could probably just run this test bench as it is and just take a look at our waveform, especially for a counter because the functionality is so obvious from looking at the waveform if it's correct or not. We know just by looking and seeing if it goes 0, 1, 2, 3, and then it goes up to 9 and then back down to 0 because it's a BCD counter. So we know the behavior is going to be pretty obvious to us if it's correct. So we don't necessarily need to make this a self-checking test bench. You could if you wanted to, but it's not really necessary. So I would probably just leave it like this and run the BCD counter on this, and then I'm done. And I can just look at the waveform very easily. I don't want to make more trouble for myself if I can just look at the waveform and figure out if I'm done like that. Only in more complex designs where it's not so obvious if you're done or if your design is correct would you actually make it a self-checking test bench.
Okay, then yeah, that was my question. Like, I didn't know what to put here.
You don't always have to put
Like,
everything.
okay.
You can just leave it and look at the waveform yourself if it's sufficiently simple. Again, if it's super complicated, make it self-checking. But I mean, I could make this one self-checking too. It would take me longer to do that than it would to just look at the waveform for 5 seconds. Um, I could, if I wanted to, write up a test vector file, type 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, load it into a series of test vectors, and then every negative edge of the clock check, compare the read-in value from the test vector file to the actual output of the BCD counter, check it against count, compare, see if it works, if it doesn't. But it's it's really unnecessary for this simple of a module. You would probably want to do that for the total top level module. You might want to do that, not for this one. Okay. Any questions?
Yes. Sorry, I'm just waiting for my code to load really quickly.
No worries.
Oh, okay. So if we were like writing a self-checking one, and then that would be like always at pause edge clock, begin, and then we would have like CLK reset and then like expected count or whatever in our test vector.
Yeah. Something like in and one tick, and then you can go ahead and apply your test vectors. So in this case, there are no inputs to apply. So I need to think of a different example. Maybe like, I guess we'll say input signals, output signals. It's going to receive the value from test vectors index vector num. And so you'd have all of your input and output signals. So I guess input signals to test, and then output signals expected would go here. So you load those into whatever your corresponding logic signals would be, and then you would have the checking part. So this is the self-loading part, the part where it loads in the test vectors. And so obviously you need to have, besides just your internal logic, you'll need the test vector signals. So you need things like what's it called, the vector num, which is the current vector you're on. Eventually, we're going to need something to count how many errors there are if we want to make this self-checking. And then we'll also be needing the part of the test vector, which is going to be the thing that actually holds all of my test vectors. So I can go ahead and do, let's see. I guess if my input signals were 4 bits and my output signals were 7 bits, I'd have an 11-bit test vector file. And then I would specify how many of these I want, which is probably a lot. And then this would be what goes over here. And then down here in this next always block, like you mentioned, we can say always at. And then here we can do it at the negative edge of the clock. And then in here we can write the code to check against what we expected to get, starting with, if not reset, then you can actually start executing stuff. And then in here would be all the stuff to check. You can take a look at that as well on the examples you guys have provided for the self-checking test bench. But yes, that's pretty much the flow.
Okay, so like just to make sure I understand. So for this one, we really would just have at the pause edge clock, our test vector file would just pretty much have like 1, 2, 3, 4, 5. So we'd have logic, like test. We wouldn't even have a bit width for the logic because it's only 1 bit.
Yeah, so you would have something like this. You'd have expected,
Yeah.
or I guess I'll do CNC expected.
Or it's 2-bit, 3 bits, right?
The count is 4
'Cause it's
bits.
0 through 9. Oh, it is 4 bits?
Yes,
I thought it
because-
only went up to 9. Oh, yeah. Okay. Yeah, I see.
So in this
Okay,
example,
yeah.
there wouldn't be any inputs to test, quote unquote,
Right.
just expected outputs to test against. And so, yeah, that would be what goes in here. And that's pretty much it. The only extra thing, again, is checking it against the actual values for the DUT that would go in this always block.
Yeah. Okay. Thank you so much. That's very helpful.
Very welcome. Any other questions on that?
No questions from me.
You guys got any other general questions?
Wait, sorry. Why would wouldn't it be logic 3:0 for the test vectors? The
Oh,
test
yes.
vector.
I just forgot to change it because the example I did was like 11 or something. Yep, that's right.
Okay, now I have no more questions.
Yeah, and if we were doing test vectors, we would need to make sure that we don't forget to actually read in all of my test vectors using the read mem either H or B. I'm going to do H for this one. And you'd be reading in from, your file into whatever array it is that you're going to be using as your test vector array. And that should be it. Just remember that if you're using readmem H, when you write your text file, that it's in hexadecimal, and if you use readmem B, that it's going to be in binary. I think that's about it. Any other questions? What did you guys cover in class today?
We really just did the what's it called? Like the midterm review?
Oh, okay. So you were doing that the whole class?
Yeah, she like went through all the answers and
Okay. All right. Any other questions about tonight's homework? Or did you guys say it was due tonight, or was it pushed back?
it was pushed back
Okay.
to Wednesday.
Yeah. So any other questions on that?
So I did have not like specifically about this example, but like if we weren't using the test vector file, and we like just wanted to manually I'm trying to see this example. Like if we just want to like manually put in some tests here, like without reading in a file, um like we'd have to reset in between each one,
No, you've got to
right?
reset.
No? Okay.
It depends on how you
Oh
want
yeah,
to
I
do
guess.
testing. But like for example, for this one, the way I'd want to test is I would just want it to run. But in a different example, it really just does depend. Typically, you don't have to reset every single time. Um, and if you do need to like pulse the reset, that's fine. The easiest way to do that is just you would make like an initial block. Like if you didn't want to do a test vector file, you could just do like an initial block for all of the things that you want to basically force high or low, instead of typing force in model sim or doing like a test vector file. So you could say initially A is going to be 1, and then you're going to delay some period of time. You're going to delay 40 simulation ticks, and then A is going to be set to 0. And you could also, if you wanted to, change B in the middle of this initial block, or in a separate initial block, if that's easier for you. You can do that too. Just don't try and have separate initial blocks force the same thing to different values at the same time. That would be a little weird. So, I could do this and then wait 20 simulation ticks, and then set B equal to 0 again, wait another 20, and then I can set B equal to 1 again. So now I have A starting at 1. Oh, A starting at 1, and then after 40 ticks it goes to 0. And then B starts at 1, goes down to 0, then goes back up to 1 at the same time that A goes down to 0. So now I don't have to force the things, but also I don't have to write a test vector file. So I could do it like this if I wanted to. This is typically if you have lots of inputs. Using a test vector file is just easier. Only if you have a small number of things you're trying to force would I recommend doing it this way. It's just not that practical all the time. Any other questions? How are you guys feeling about your lab projects?
It's coming along.
That's good.
It went over, and then me and my lab partner got the generate random number generator
Yep.
module to work. Yeah, we just decided to make it like just counter based because the other one was just like that's just we don't want to over engineer it.
That's very fair. Don't make it don't make it that hard. Yep.
Mm-hmm.
What about you, Shauna? How's your project coming along?
It's okay, I guess. I'm still like, okay, can we talk about like how much do we need to test before we put something into the board? Because like if I can run it, like if it compiles and I can run the waveform and everything, like is it safe to put it on the board or
I
like
mean, you can put it on the board. It's just like you could do it without a test bench if you really wanted to. If you were that confident in its behavior, it's not gonna like make the board like blow up or anything. But
okay, that's what I'm worried about. I'm worried
no,
like
you're not
something
worried about
will
that.
like run an indefinite loop and like blow up my board and then I'll have to pay $300.
No,
So
you're not gonna blow up your board.
I haven't tried anything on the board yet.
No, you can try whatever you want on the board. It's not that serious, I promise. It's not like
Okay, they made me scared, like, when it was like, "Test everything," and so then I'm like, "Oh my gosh, how much do I need to test it?" So
no, it's not about making the board blow up. It's about saving yourself hassle because if you just go straight to the board, you are going to have a lot of bugs to work out. Because not only do you have to work out um, the bugs that you would have had to work out if you simmed it, but you also have to work out hardware bugs, thinking about stuff in terms of actual physical hardware instead of nice simulations. So there's two levels of debugging you have to do: software, or not software, sorry, simulation level, and then hardware level. And then if you try and go straight to the FPGA board, you have to do both at the same time. It makes your life a lot harder, which is why we don't recommend doing that. You can, but I would only really do it for very simple modules, not for bigger ones, more complex ones. I wouldn't recommend going straight to the FPGA for those. It would just make your life harder.
Is the FPGA only 300? I swear it was more expensive, right?
Uh, Probably more. Yeah, I don't remember how much
Yeah.
one, but these
scary expensive.
were I think it's like 500, maybe more. I don't remember. You can get some for pretty cheap, like well, relatively cheap compared to the ones that you guys have in lab. There's these little ones that the CPE 100 lab students use. You guys didn't have to take CPE 100 lab because that's just used for people who aren't CPE majors or EE majors. But CPE 100 lab has these little tiny boards, they're like this big, called the DE0 Nano board. It costs about $100. You can do all the same stuff that you can on your big board. It's just a few less switches, a few less push buttons. Still has like a VGA, for example, a VGA connector. It's pretty useful and very small, and not nearly as expensive as those other bigger boards. There are a bunch of other smaller boards, not just from Altera, but also from like Xilinx that you can use for FPGAs that are pretty small and relatively cheap comparatively. Any other questions for me?
I have no questions. Thank you.
No worries.
Nope, nothing for me.
So, are your guys' mid-project reports coming up soon?
They were due on Sunday.
Oh, they were already due. That's
Yeah.
funny. I thought they would have been due like in class.
I think it might be because of we don't have class on Friday.
Oh, yeah, you know what? That's right. Forgot about that.
Wait, when is the whole thing due? Is it December like 5th or 7th or something?
Probably? I don't know. I do know you obviously have to finish it before the junior design competition, and I think that's like around there.
Yeah, I think we only have like 2 more weeks. It's a little scary.
Tell me about it,
Yes.
man. This semester has gone by at lightning speeds. Um, there we go. There's the 2022 flyer. Looks like your guys' competition is on the 8th. So theoretically, that's your actual due date. As for when your in lab report is due, I don't recall, but um, honestly, I don't think they'd care that much if you turned it in like right before the junior design, or even like right after. I don't think they mind that much. Um, they don't. They're not that strict on due dates, at least if you're keys. Well, you guys have Smith, yeah.
Yes.
I don't imagine he'll be that uptight about the dates if you guys need to have an extra day about like getting your report finished or your final report or whatever. As long as you have your actual project done and you present it in the junior design competition, it won't matter that much. Are you guys excited to work on your projects and to do the design competition, or nervous, or annoyed, or tired?
I'm excited to
I
be
will
done.
be
Yeah.
happy. Oh, you're excited? That's great. Good
No,
man.
to be done. To be done.
Oh, I was like, I will be happy if we just have something that works at the design competition.
Same.
I mean, yeah, making
I have
something
very
fun.
like I think this would be a lot more fun if we had more time and like not other classes going on. Like I find this to be really interesting and it's like really cool when I code something that works and I feel like I'm learning a lot, but it's just like the time constraints is making me really anxious. So that's kind of what I'm feeling.
Yeah, Yeah, no, I understand it. It can be quite a bit, especially when it's like, oh, I have to put more work into this class than some of my other classes. This is crazy for a 1 credit lab for my project. But
Exactly.
it's it's a lot of work, but it does pay off if you make a nice little design, something to put on your resume, especially if it's practical or if you win a spot in the competition as well. Um,
What are you doing for the senior design? You had like a car or something I saw?
oh no, that was for one of my classes. That's for my robotics class. Um, for my senior design, this is my first semester, so me and my partner picked our project earlier in the semester, and we are working with a technical advisor who is building, um, funnily enough, is building robots unrelated to the car that you saw. um, for use, and those robots are going to be used for high school CS students to practice code on and run a bunch of cool stuff. And the idea is for the robot to have just a bunch of sensors for them to mess around with. And so we're going to be designing one of those, or we're designing one of those sensors. It's a wind sensor, which is called also called an anemometer. And typically that's not a particularly hard thing because you can normally just like buy an IC, connect a bunch of stuff together, put it on a PCB, you're done. But we're actually going to be doing it without using any ICs at all. So just discrete components, resistors, capacitors, inductors, and transistors, things like that. So it's definitely an interesting project. It's quite fun and it's very informational about how to do analog design stuff. So that's what I was hoping to get out of it, and I am. So I'm pretty happy about that.
That sounds really cool.
Yeah, we're definitely not going to win. It's not showy or anything, but I'm happy with what I'm going to get out of it, so I don't mind. There are some pretty cool projects that some of my peers are talking about, though. Like one of my friends, him and his team are working on a set of glasses for anyone who's visually impaired that will speak to you and tell you about obstacles in your way and like where you're walking, things like that. So it sounds pretty dang cool to me.
Yeah, that's that sounds really amazing too.
Um, let's see. We got about 4 minutes left. Did you guys have any other questions for me? Doesn't have to be related to the course content. If you did, random questions is fine too.
Are you using in your internship, are you using a lot of the Verilog? Or you said it was like a different HDL?
Uh, actually, right now what I'm doing is I'm learning about topics and then creating tutorial videos on those topics. So I've just gotten my first assignment, or I just finished my first assignment, which was to learn about Aldex tool flow for one of their tools, Alent, and how to perform clock domain crossing analysis. I might have very briefly mentioned clock domain crossing to you guys in one of the previous officers. I don't remember if I have. Do you guys remember anything like that? It's fine if you didn't. I just don't remember if I've mentioned it before.
I'm not sure. It sounds vaguely familiar, but I can't recall.
That's okay. It's essentially just when you have different systems that run with different clocks that are asynchronous to each other. So not like using a clock divider and you get like a 1 megahertz clock down to a 50 kilohertz clock. That's not what I'm talking about. I'm talking about two completely separate systems running off of two completely different clocks asynchronous to one another. And at the hardware level, you want to transmit data between them. And the problem is when you transmit data, you could be changing the data right when you're trying to sample it, right when you're trying to sample the data. And that leads to metastability, like we've discussed a few times in office hours. You can't be changing the data on the input of your flip flop while your clock edge strikes, or within that aperture time around the clock edge, because that leads to metastability. And so to solve that issue, you have to create what are called synchronizers or synchronizer circuits, which are used to essentially prevent the data input from one clock domain, so that's just your system running off of one clock, into the other clock domain. So it's preventing that data from changing while this guy's sampling. There are a multitude of synchronizer circuits that do this. And so my previous week, I made a video about just generally speaking how to go through the process of um, figuring out if you have a clock domain crossing issue that you need to solve, how to go through it, and then how to add in like a circuit to synchronize stuff. And now my next project is going to be working on many different types of synchronizer circuits that their software, their tool, ALANT recognizes. So like enable synchronizers, multiplexer synchronizers, brute force synchronizers, handshake synchronizers, first in, first out, a whole bunch of them. And so I'm going to be learning about those and making videos about those. So that's what I'm doing now. Which is some pretty interesting stuff, at least for me. I think it's interesting.
Yeah, that sounds difficult.
It's not that bad, not really. It's just different. Don't really learn you learn a little bit about it, but you don't learn a lot about it in your like undergraduate level classes. Any other questions before we end it for the night?
Did you oh sorry, Shana, but did
Oh, no,
they
go
okay. Uh did they make you go to do YouTube, or did you want to do YouTube? Or just videos?
Oh, well, that was kind of the what's it called? That was kind of like the expectation when I was brought on, that I would be making those tutorial videos as an intern, mostly for two purposes. The first primary reason is because they have a lot of users that simply don't know all of the ins and outs of their tools, or are unfamiliar with specific aspects of those tools, and they don't have tutorials covering them very in depth. So they have me and another intern there working on making videos for in-depth guides on how to use those particular aspects of their tool. So that's the main reason why they're using it. The second reason why they're having me do that is so that I can gain familiarity with their tool, so that if later on I was to work there full time, I would be able to more easily fulfill any roles that I have. And that's like the basic idea of why they'd have me do that. Just so I can gain familiarity with stuff, and they can also get basically tutorials or help guides for their users. Did you have a question, Shauna?
Nope, I'm good.
All right, cool. All right, I'm gonna go ahead and end our office hours today. Tomorrow, I will probably have my mic. We'll see if I remember to bring it. But thank you guys for coming in, and I'll see you guys tomorrow.
Great, thank you.
Thank
You're
you.
welcome. See you guys.